So today we will start this three-phase transformer. The syllabus contains construction of various types. There are two types of construction that will be discussed. Next is operating characteristics of star-star, star-delta, delta-star, delta-delta, open-delta connections. Okay. So these are different types of connections of three-phase transformers. So we will discuss the operation or operating principle of these type of transformers. And then is vector groups or phasor groups. Okay. So let us discuss some introductory concept. So first of all, we know that in modern power system, most of the electrical energy is generated from three-phase generators. Okay, and this three-phase generated power is transmitted and then distributed through three-phase circuits. Okay, and while we are transmitting this power from this generating station to the consumer premises, there are then during this transmission we require to raise or to lower the voltage levels several times for economical reasons. Okay, and we can do that operation, that is either step down or step up this voltage level using transformer. So since we are generating power in three-phase circuit or distributing or transmitting this power through three-phase circuits, then obviously we will be requiring some three-phase transformer. Okay, so now three-phase transformer can be a single unit, or we can use 3 units of single phase transformers as a three-phase transformer bank. Okay, one three-phase transformer can be built, or we can use 3 identical transformers to act as a three-phase transformer. Okay, so this when three identical single-phase transformer are used as a three-phase transformer, normally that arrangement is called a three-phase transformer bank. Okay, you can see from this diagram here 3 identical transformers are placed side by side and they are connected to act as a three-phase transformer bank. Okay, so here this type of arrangement is known as three-phase transformer bank. So we can use one single unit, or we can use 3 units of single phase transformer to act as a three-phase transformer. Okay, next is construction of three-phase transformer is almost same with that of single phase transformer. The only difference is the construction of transformer core or the magnetic core. Okay, in a transformer, single phase transformer, the core is meant to be hold or carry only 2 windings, that is one high voltage winding and one low voltage winding. But in case of three-phase transformer, the core has to hold 6 coils, sometimes 9 coils. In case of zigzag or interstar connection, the core has to hold 9 coils. Okay, for star or delta connection, it has to hold only 6 coils. This is a single phase transformer core. You can see there are 2 legs or limbs and 2 coils are placed separately, but in actual transformer it is not so, you know that. And this is a 3-phase core showing 6 coils, 3 primary windings and 3 secondary windings. Okay, here also the primary and secondary windings are shown separately, but in actual case, first the low voltage winding is placed nearer to core, and then some insulation, and over that the high voltage winding is placed. So here the main difference is the construction of core. So other than that, everything else like winding construction, insulation construction, tank and other accessories are exactly same in case of a 3-phase transformer as that of a single phase transformer. Okay, so only the core is differently built. Like single phase transformer, the construction of core of this 3-phase transformer are also 2 types. One is core type, another is shell type. So what is this core type construction? You can see the diagram. So here the 3 windings, or actually 6 coils, are placed on 3 limbs. Limb 1, you can see first the low voltage winding is placed, then over that low voltage winding the high voltage winding is placed. So this is for R phase, first low voltage winding, then this is for high voltage of phase R, over that low voltage winding is placed. In this way the other 2 phases are also placed onto different limbs. Okay, so this is R phase, this is Y phase, this will be Y, I'm sorry. So this is Y phase and this is B phase. Okay, so in all the 3 limbs, first the low voltage winding is placed, that means nearer to the core, and then over that low voltage winding the high voltage winding is placed for all the 3 limbs. Okay, so each limb contains both high voltage as well as low voltage winding. The terminals of high voltage and low voltage windings are taken out through bushings and other insulations from the tank. This whole arrangement is placed inside a tank and that tank is filled with transformer oil for cooling purposes and also for insulation purpose. So from that tank uh, these terminals are taken out through bushings, and then outside that tank these necessary connections are made to make it as a star or delta. Okay, the 3-phase transformers are connected either in star star or star delta or delta star or delta delta, and if there are 9 coils then it can also be connected as the zigzag. Okay, so all the 6 terminals, or in case of uh, zigzag connection, all the terminals are taken out from the tank and then the connections, the proper connections are made outside the tank. Okay, Now see the flux distribution. In this type of construction, in case of core type of construction, the flux lines, the flux produced by any winding completes its path through the other two windings. See this line, suppose this flux is produced by this winding, so it completes its path through this line as well as through this line. Okay, similarly the flux which is produced by this coil will complete its path through this line as well as this line, and it is also true for this winding. The flux produced by it is completes its path through this line as well as through this line. Okay, so that means any section of this core, either limbs or yoke, carries the flux produced by all the three windings. That means they are not independent. Now from this we can see that the yoke section, that means this section, carries most of the flux produced by all the three windings. That is why to have uniform flux density distribution, we need to increase the cross sectional area of this section. Okay, and we also need to increase the length of these limbs, this one as well as this one, which makes the height of the transformer very large, and this poses a difficulty during transportation. If the height of the transformer is very large, then it is very difficult to transport it from the place of construction to the place of installation. Okay, so to reduce the height of the transformer, we can use this kind of construction. Here two extra limbs are used, which will take a certain portion of the total flux burden through it, and thereby decreasing the height of the transformer. But as it reduces the height of the yoke as well as reduces the overall height of the transformer, but the cost of making of the transformer becomes very high, so it is not very economical. Okay, so normally three-legged transformers are used in case of core type of construction. Is it clear? Any question up to this? No question. Okay, so next is shell type construction. Here we can see, if we cut the core at this point, then it is actually just a single phase transformer. So we can say that in case of shell type of construction, three single phase shell type transformers are placed one over the other to make the three phase transformer, three phase shell type transformer. Okay, now here you can see the flux path. This section and this section are carrying equal amount of flux. This section, this section, this section, this section, all these sections are carrying total flux by 2, that is 5 by 2 amount of flux. Okay, this section, these three sections are carrying the total amount of flux, that is 5. Now tell me what will be the amount of flux carried by this section and this section. Any idea?
Sir, is it the null point?
No.
It's a sum of any two phase.
What type of sum?
Phasor sum, sir. The magnitude will be
Yes.
√3 times something.
Yes, phasor sum. But can you tell me why we have to do this phasor addition?
Sir, phi is a phasor. Phasor will represent phi in phasor diagram. So
Okay, that's true. But the actual reason is that as we are using three-phase supply, so this three-phase flux, that means this is R phase, this is Y phase, and this is B phase. So all the three fluxes will have 120-degree angle in between them. Okay, so actually suppose this phase, this flux is phi r by 2 and this flux is phi y by 2, but though they are opposite in direction, but they are not cancelling each other. They are produced by different phases of voltages which are having 120-degree angle between them. So these fluxes are also having 120-degree angle between them. So we have to do this phasor addition, right?
yes, sir.
Is it clear? So now another thing is that here the flux lines produced by each phase is completes their path.
Sir,
Yes, yes. Any
increase the
question?
size of the cursor.
Yes, tell me.
Sir, can you please increase the size of your cursor so that we can easily follow you?
No. Actually, see, only this section is carrying the total flux. The other
Sir,
sections,
he's telling. Sir, I am telling. Increase
your
the
voice
size
is
of
not
the
clear.
cursor.
Hello.
Hello, sir.
Yes.
Sir, can you please increase the size of your cursor, means computer screen, so that we can easily follow you? We cannot follow the cursors.
What? Please repeat. Your voice
Sir,
is
he's
not
telling.
clear.
Sir, he's telling that can you please increase the size of your cursor, like where you are pointing, he's not able to follow that on the screen.
Size of my cursor, but I am writing just. Is it okay now? Can you see my cursor now? How can I increase it? Okay, now see, for any winding, suppose let us consider this R phase, the flux line produced by this R phase winding completes its path through the two side limbs, okay, thereby reducing the size of this two side limbs or legs, okay, and also the yoke of this section, and it completes its path through this common section. So here all the three fluxes are almost independent of each other, unlike the core type construction. Okay, flux produced by this coil will complete this path through this path and through this path, and flux produced by this coil will complete this path through this line and this line. So only except this section and this section, the flux paths are almost independent of each other, and this type of construction is known as quasi-independent magnetic circuit. It is not completely independent. Okay, so here the flux value of these sections can be calculated using the phasor diagram. If we assume that all the three phase fluxes are having equal magnitude, that is phi r is equal to phi y equals to phi b equals to phi, say, and they are displaced from each other by 120 degree, then we can draw the phasor diagram. Here I have already mentioned that this section, and these side sections are carrying half the flux. All these sections are carrying half of the total flux produced by any one winding. Only this section and this section will carry the resultant of two fluxes. So we can find the resultant using the phasor diagram. So this is the phasor diagram. So this is phi r, this line is phi r, this line is phi y, and this line is phi b. So here we have to take phi r by 2 and the opposite of phi y by 2, because the first section is carrying phi r in one direction and the phi y in the other direction. So you have to draw the negative of phi y by 2, and then we have to find the resultant of this phi r by 2 and negative of phi y by 2, which will give you the root 3 by 2 times of total flux. Is it clear?
Yes, sir.
So accordingly, you have to provide the cross-sectional area. The middle section will have the maximum cross-sectional area because it will carry the total flux phi. The outer sections will carry half of the total fluxes, so its area of cross-section will be half of that of middle section, and accordingly the common section, two common sections will carry root 3 by 2 times of total flux. So accordingly you have to provide the cross-sectional area of the core. Okay, so that's all about this construction. Next we will discuss these vector groups or phasor groups. We'll discuss this operating principle of all these different types of transformers at the end. So first of all, let us consider the three-phase transformer connections. So how the three-phase transformer windings are connected. So as I have already mentioned, there are different types of connections like star star, star delta, delta star, delta delta, and zigzag. Okay, so we can connect any winding of a transformer either in star or delta or interstar, or that is known as also zigzag. So in case of a bank of three transformers or a three-phase transformer, as I have already mentioned that if it is a single unit of three-phase transformer, the connections are made outside the tank, so you can change the connection anytime. Okay, all these 6 terminals are taken out from the tank through these bushings, and the connections are made before it is connected to the system. Okay, power system. So here this a bank of three transformers or a three-phase transformers may have its primary and secondary windings connected in star, delta, or zigzag. Okay, and these type of connections are designated by the symbols star by Y, delta by D, and zigzag by Z. Okay, So these are the symbols to denote the different types of connection. And this zigzag connection is also known as interconnected star or simply interstar. In representing a three-phase transformer, the high voltage winding is indicated by capital letter and low voltage winding by a small letter. Okay, so suppose a transformer having its primary winding connected in high voltage winding connected in star. So you have to write first the capital Y, then if its low voltage winding is connected in delta, then you have to write YD. Then you have to write in which phasor group it belongs. That we will discuss later on. First of all, the connection of two windings. If it is a delta Y, then first you have to write capital D, that means high voltage winding in delta, then low voltage winding in star, dy. Then you have to write the group. Okay. So dy represents a three-phase transformer with high voltage in delta and low voltage in star. Now, suppose YY transformer, that means high voltage winding as well as low voltage winding both are having Y connections. Now this line to line voltages, there are three line voltages in case of this three-phase system. So if the high voltage winding is star connected and low voltage winding is also star connected, then you will have three line EMFs. Suppose if the lines are denoted by the symbols A, B, C, that is the three phases, then you will have three line EMFs VAB, VBC, VCA, same as in case of low voltage winding VAB, VBC and VCA. So now in different types of transformer connections, these line EMFs and these high voltage line EMFs and the corresponding low voltage line EMF may or may not be in phase or out of phase. May or may not be in phase. What is the meaning of this? That means this VAB and V small ab, they are either in phase or not in phase. Okay, if they are in phase, then the angle between them will be 0 degree. If they are not in phase, then there will be some angle in between them. That we have to denote using certain technique. Okay. So this time phase displacement can be expressed either in degrees or by a much more convenient method known as clock method of angle designation. So what is this? Here you can see the dial of a clock where this minute hand, which is having the maximum length, is denoting the high voltage line phasor, and the hour hand, which is having the smallest length, denotes the low voltage line phasor. Okay. So according to this method, the high voltage line phasor is considered as the minute hand, always set at 12 o'clock, that is 0 hour. So this will be our reference. That means the minute hand is always set at 12. So that will be our reference. With respect to this 12 hour or the reference line, what will be the position of this low voltage EMF, that we have to denote. Okay. So if it is, suppose in this diagram it is showing 11. Okay. So 11 means this low voltage winding. We have to assume that phasors are rotating in anti-clockwise direction. So if this is the reference line and sorry, hello. So if this is the reference line, the low voltage line EMF line phasor is 30° ahead of this high voltage line phasor. So suppose if we have one Y delta transformer, so Y star connected in high voltage winding is star connected, low voltage winding is delta connected, and this low voltage line EMFs are 30° ahead of high voltage line EMFs, all the three line EMFs. Okay, so then you have to write YD11. So this is one phasor connection. So from this symbol we will understand that the high voltage side winding is star connected, low voltage side winding is delta connected, and the low voltage line EMFs leads the high voltage corresponding high voltage line EMF by an angle of 30°. That is the meaning of this symbol. Is it clear? Any doubt? Anyone? Is it clear or not?
Sir, repeat once, sir.
Okay, I will discuss. I am going to next slide. It will be more clear. Okay. So for two winding three-phase transformer, as per the clock method, first symbol represents HV winding connection. Second symbol represents low voltage winding connection, and the third symbol is for the phase displacement between high voltage and low voltage line EMFs, expressed as clock hour number. Okay, so this phase angle difference is in between line EMFs of high voltage side and low voltage side, not the phase EMF. Phase EMF for any particular phase is always in phase. R phase high voltage winding, R phase low voltage winding, they are always in phase. Similarly, Y phase line EMF, Y phase high voltage winding and low voltage winding, phase EMFs are always in phase. Phase EMFs means the EMF induced in any particular coil. Okay, line EMF means after making the connections, what you are getting across any two lines. Suppose this is one star connected winding. So this point is A, this point is B, this point is C. So this EMF is the phase EMF, this EMF is the phase EMF, and this one. But the line EMF is in between A and B, or B and C, or C and A. Okay. Correspondingly, you will have this similar connection or similar line EMFs in case of low voltage winding. So VAB and V small ab, these are two line EMFs. They are either in phase or not in phase, but VA and VAA, they are always in phase. Similarly, VB and VB, they are always in phase because these two windings are placed on the same limb or leg of the core. Okay, similarly, VC and V small c, they are always in phase. Is it clear? This phase EMFs and line EMFs, is it clear or not? So as we know that the phase EMFs are always in phase, so we have to find whether the line EMFs are in phase or not. If they are in phase, then the angle will be 0, and if they are not in phase, then we have to denote this angle by some method. So here we will follow this clock method. Okay, so our hand is denotes the low voltage line EMF, minute hand denotes the high voltage line EMF. So if they are in phase, so in that case this our hand will coincide with the minute hand. So angle is 0 degree. So we can write one transformer connection like YY0. Okay, so the first letter denotes the high voltage winding connection, second letter or the symbol denotes the low voltage winding connection, and this third symbol denotes the angle between line EMFs of these two windings. That means angle between VAB and V small ab, that is 0 degree. Similarly, VBC and V small bc, that is also 0 degree. Okay, now if we have a transformer with YY6 connection, that means this our hand is now here. What is the meaning of this? The meaning is that high voltage winding is Y connected or star connected, low voltage winding is also Y connected or star connected, and the angle between VAB and V small ab is 180 degree. They are totally out of phase. Is it clear now?
Yes, sir.
So remember that while expressing this in transformer connection using these phasor groups, we are expressing the angle in between line EMFs, not the phase EMFs, because the phase EMFs are always in phase. Okay.
Sir, is there any like chance that the hour hand is in between two numbers, like between 8 and 9, suppose?
No. That is not possible. Okay, so let us consider one example. Here I have considered YD11. So it represents a three-phase transformer with high voltage winding in star connection, low voltage winding in delta connection, and this low voltage line phasor at 11 o'clock means 30 degree ahead of 0 hour position of the high voltage line phasor. So here we will consider that the high voltage line phasors is the reference, and with respect to that the position of low voltage winding line phasor we have to determine. Okay, so if it is YD11, that means low voltage line phasors are 30 degree ahead of the high voltage line phasors. If it is YD1, that means the low voltage EMFs, line EMFs lags the high voltage line EMFs by an angle of 30 degree. Isn't it?
Yes, sir.
So that is how we will express different phasors, different phasor groups. Okay. Now for a three-phase transformer, in addition to the knowledge of high voltage and low voltage connections, the phase angle between the high voltage and low voltage line EMFs must be known. So the connection with the connections, we also need the angle between angle between the line EMFs of the two windings, high voltage winding and low voltage winding EMFs. Okay, depending upon the type of connections and phase displacement between the high voltage and low voltage line EMFs, there are different phasor groups. Okay, Each group is characterized by a different phase displacement. And what are the groups? These groups are, okay, I will discuss the groups later on. First of all, how to differentiate between these different groups. Okay, so first of all, we have to know certain conventions. Let us see that here in this diagram you can see, consider one leg. So here the high voltage winding and the low voltage winding belonging to the same phase. Suppose this is phase A or R. Okay, so R phase or A phase high voltage winding as well as low voltage winding, they will be wound over the same limb or leg of the core. In this diagram, though we are showing separately the two windings, high voltage winding then low voltage winding, but in actual transformer you have to place the low voltage winding nearer to the core, then over that low voltage winding you have to place the high voltage winding. That is from constructional point of view, but here we here the point is that you have to place the same phase windings on the same link. If the high voltage winding and low voltage winding are on different leg, then there will be some phase angle difference. That is not permissible. So A phase high voltage winding and A phase low voltage winding must be placed on the same link. That is what this diagram is showing. Okay, so this leg is for A phase windings, both high voltage and low voltage. This leg is for B phase windings, both high voltage as well as low voltage, and this leg is for C phase windings, both high voltage and low voltage winding. Okay, so here the terminals are A1 and A2, capital A1 and capital A2 for high voltage windings, and small a1 and small a2 are the terminals of low voltage winding. Okay, so as we are placing the two windings on the same leg or limb of the core, that is why the phase EMFs are always in phase. Okay, naming of the terminals has been done according to their polarity. That means if we consider A2 terminal as positive with respect to capital A1, then small a2 terminal will have the same polarity, that means the positive with respect to small a1. That means if a2 is marked dotted, then small a2 will be marked dotted. See the previous diagram. See, this is the dotted terminal. If we assume this is positive terminal, then this a1 will be positive. Same is for other windings. Okay, so here if we assume capital A1 as positive, then the small a1 will also be considered as positive. Now based on that, we can draw the three windings on a horizontal plane. So here A1, B1, C1 all are having same polarity. Similarly, the small a1, small b1 and small c1, they are also having the same polarity. Okay. Now as these windings are supplied by three-phase voltage system, suppose VA, VB, VC are the three-phase voltages which will be connected to the input side, that is the high voltage side. So these voltages are phasors, so they are having 120-degree angle between them. So accordingly, the EMF induced in the high voltage winding and the low voltage winding of the transformer, they are 120 degree apart from each other. So these coils, to enhance the visual appearance, we can draw according to their orientation given by the supply voltage system. Okay, so if we take the A phase as the reference phasor drawing vertically upward direction, so we can draw A1, A2 vertically having same orientation. We have to draw the low voltage winding. Similarly, B1, B2 is drawn making an angle of 120 degree with A1, A2. Here this will be the actual position of B1, B2, and this angle is 120 degree. So B1 will be connected to A1, this point. Okay. Similarly, position of C1 will be here. So this is actually C1. So here this angle and this angle are also 120 degree. Same is true for the low voltage windings. This one, and this one. Is it clear?
Yes, sir.
Okay. So the high voltage winding is assumed to be the primary and low voltage winding the secondary. That means while we are going to draw the phasor groups or phasor diagram for different phasor groups, we have to follow these conventions. Then that is, we have to consider the high voltage winding is the primary and low voltage winding is the secondary winding. Okay. The position of high voltage terminals A2, B2, C2 is assumed fixed for convenience in the top, bottom right and bottom left corners respectively of the equilateral triangle A2, B2, C2. So that means the terminals of high voltage side B2, A2, B2, C2, their positions are always fixed. Okay. Whatever may be the connection, if it is delta connection, then A2, B2, C2 will be here. If it is star connection, then also A2, B2, C2 will lie at these positions only. Okay. Now, based on those conventions, we will be able to draw the different phasor groups. And here we have 4 phasor groups in our syllabus. And those are group number 1 with 0 degree phase displacement, and the possible connections are YY0, DD0, DZ0. YY0 means high voltage in star, low voltage in star, and the line EMFs are having 0 degree phase displacement. Similarly, DD0, both high voltage and low voltage are in delta. DZ0 means high voltage in delta, low voltage side is in zigzag connection, and the line EMFs are in phase. That means there is 0 degree phase displacement. Okay. Next group is group 2, which is 180 degree phase displacement, YY6, DD6 and DZ6. 6 means the hour hand is at position 6. Okay. So the high voltage line EMFs and low voltage line EMFs are 180 degree out of phase. Group number 3 is minus 30 degree phase displacement. Minus means lagging. Okay. So YD1, DY1 and YZ1 are the possible connections. And group 4 is positive 30 degree phase displacement, that means leading. Okay, minus means lagging, positive means leading, and the possible connections are YD11, DY11, YZ11. So these are 12 phasor groups in your syllabus. Okay, so in next class we will consider this in detail, and we will learn how to draw the phasor groups and phasor diagram, and from the phasor diagram how to draw the connection diagram. Okay. In case of YY or DD connection, 6 coils will be given. In case of DZ or YZ connection, 9 coils will be given. 6 for zigzag connection, and D or Y for D and Y, 3 coils will be given. Okay. Okay, time is over today up to this.